Hello and welcome to another video in my first steps in R for flow cytometry data analysis. Today I'll be looking at gating using the package flowWorkspace, be looking a little bit at errors and how to avoid them, and a little bit more on statistics and visualizations. So let's get started. In RStudio we will load, compensate, transform and clean the data as usual. First I will load the necessary packages. Then I will load the data. I will produce a list of files from my folder, remembering to use the ignore case command. This is to ensure that case sensitivity doesn't affect the files I find. Next I'll load them into a flow set called fs. Next I will compensate them using the compensate command. Next I will clean them using flowAI. So whilst this is going, I'll let you know that first we'll be looking at manual gating, and then secondarily, we'll be looking at automated gating. Next, I will transform the data using the estimate logical command. To find out which parameters I want to transform, I can highlight one of my files and look into it, and I can see that I want to look at the parameters 3 through 10. So I will change the parameters here, and I will only transform those ones. So once I've estimated the transformation, and apply it using this transform command here. Next, I'll visualize the transformed file, make sure that it looks all right and acceptable, using the autoplot command from ggcyto. It should appear over here on the right. You can see this looks fairly acceptable. Looks like a typical plot. I can see CD14 here, MHC class 2 expression. This looks alright. So if I want to do some gating, some manual gating, first I need to visualize the file to see where the gate should go. So I'll be using the ggcyto command. In a later video, I'll go through how to use ggcyto properly. And then from here, I can estimate where I want to put a box. So what I'm going to do is create a rectangle box around my lymphocytes. So first, I want to create a gating set. So flowWorkspace is a package that mimics the gating hierarchy you would normally use to analyze your flow cytometry data. So similar to what you would have, say, in Diva or FlowDraw, FCS Express. Now, FlowCore, the core flow cytometry analysis package, does have something called filters, but this way, using these gating sets in flowWorkspace, you'll recognize the analysis more easily. So first I want to create an empty gating set using the gating set command. Then I want to produce a rectangle. So what I'm going to do is I'm going to make a rectangle gate on my forward scatter parameter. I want to call it non-debris. So basically, this is going to create a rectangle from the 15,000ths channel to infinity in forward scatter. So that should be around here, all the way to the very edge of the plot. And then I'm going to use this gs_pop_add command to apply this to my gating set. So I should point out that flowWorkspace in the last few months, and I'm recording this in July 2020, has had a lot of changes recently. And a lot of the commands have changed to make them more understandable. So if you look at some older tutorials, they won't work anymore. So this GS gating set population addition will add to my gating set, which is GS, which I have over here, rectangle 1, which I've just created, and the parent is root. So root is basically the top level of my data, i.e. all my data. And you can see it says I now have 2 gates. This recompute command recalculates all the statistics based on these gates, and that's done. So now if I use this gating set get population paths, what that will do is tell me what gates I have. So I currently have root and no debris, and I can visualize them using ggcyto. So using ggcyto, I can look at my forward scatter and side scatter and include this is the level of dots, the level of resolution, and I can add the geometric gate non-debris. As I said, I'll go through later in another video how to use ggCyto properly. But this will visualize my gate. So you can see I've got a red line at 15,000 channels, and everything to the right is gated as non-debris. If I want to look at some statistics, I can use the command gating set population get statistics, and this will produce a count. And we'll talk more about statistics later in the video. So next, I want to do some singlet gating. So I want to do my forward scatter height versus forward scatter width. So the first thing again I want to do is just look at the data to judge where I want to put the gate. And I have an error saying I cannot find my forward scatter height. Now why is that? So if I highlight my file, press Control Enter, it will give me the information of my file, and I can see that this file does not have forward scatter height or width. In fact, it has no way to gate the singlets at all. So that's a little bit of a disaster. So I think we should just move on to the automated gating and with a different data set. But if I were to do this, I do exactly the same again. I make a second rectangle gate with the coordinates. The coordinates here are wrapped in C, and this C means that I'm grouping multiple values together. So if I'm creating a box, I need to have the X and Y coordinates. So that's what I have here. I use the gating set population add command, and I apply it. The parent this time is not root, it's non-debris. I give it the name singlets, and then I can recompute it. Okay, so just before we go to automatic gating, which is probably what all of you want to do, there's a few more useful commands. So if you type in plot in your gating set, it will produce a hierarchy of your data, of your gating structure. The statistics we've already seen, but there's other statistics you can do, and you can select certain populations and you can change the statistic. The default is count, and there's also percent, and you can also create statistical functions to apply to this, but we'll go through that later on. Okay, let's look at automated gating. So what I didn't say earlier, by the way, is I'm using files from Flow repository again. You can find links to these in the bottom, as well as a link to the script that I'm using now. So we're going to do some automated gating. So we're going to do exactly the same as we did before by loading the data. So I'm just going to clear my workspace to make it simpler for you by using the little brooms. And I'm going to list my files and load them to a flow set. So you should note that there's a new command here called alternames equals true. So I did a test run of this and had quite a few issues, and I was trying to work out what the issues were. And this didn't cause the issue, but this is something you should bear in mind, that R doesn't like spaces. It particularly doesn't like forward and back slashes. So what you can do when you're loading your data is by using this alter.names equals true command, it will replace all the non-standard characters with dots and X's. And so this might make the data, the parameters look a little bit strange, but it'll behave better in R. So I'll be using that this time. Also, if you're using a tune like I do, the tune allows you to use forward and back slashes in the names, and that can cause some real issues. And what you can also do is something called empty values command, which you can look up in the help file, and that will allow you to load your tune data. Okay, so again, we will compensate and clean the file. So if memory serves me right, the compensation doesn't work very well for this one, and I have the wrong command, so I'm just going to copy. I'll just use this one here because it's the same, and it's going to give me an error. So this error is caused by something. Let's find out what the error is caused by. So let's look at the data. Flow set. I'll just type NFS down here. Flow set. And I can see that this is the name of my parameters, but this is the name in the compensation file. And you can see they're different. Now, how an FCS file has a different compensation matrix to the names of the parameters, I have no idea how that's happened. So to fix that, we need to change the matrix. So let's have a look at the matrix. So I'm just going to copy this command from earlier and bring it down to the bottom because it's in the wrong place. So I know that's not going to work. So what I need to do is produce an empty matrix. So I can produce a matrix using this spillover fs spill command. And if I then type in matrix, I can see it's here. And I want to change these names to match the names in my file. So the easiest way to do that is just to copy these and apply them to my matrix. So I will use the column names R command in matrix. So what this is going to do, it's going to overwrite the column names in matrix with something of my choice. So I will use the C command again and paste in my values. But I obviously don't want the forward and side scatter, so they don't exist in my compensation matrix. And sadly, these all need to be bracketed, so it's going to take me a few seconds. I'm going to speed up the video to make it more understandable for you. Okay, as you can see, that took a bit longer than it should have because I'm using a giant cursor, which makes it very hard to highlight the right things. But I'll use this column names. Oops, I can see an error there. There we go. Press Control Enter. And if I look at the matrix again, I've got new headers on my matrix, and that works. So I can change my compensate command to compensate, flow set, and matrix. And that should work. As you can see, as usual, the matrix is empty, so there was no point in doing this. But it's a nice thing to show you through the troubleshooting steps, especially if you're analyzing other people's data like I'm doing here. So again, we're going to use flow AI and then transform the data. Okay, and also for your information, I've only done 2 files here, using the subset square bracket command, just so it doesn't take too long, because you can see over here there was actually originally 240 files, which would have taken the rest of the day. So we do the transformation by using the estimate logical command. We can choose the parameters by highlighting the file. There we go. Press Control Enter. Oops, I broke my brackets there using my giant cursor. Not recommended ever to use a giant cursor. Control Enter, and I can see that I want to transform parameters 4 and 6 to 12. So to do that, I use the C command again. So this allows me to group numbers together. So I'm using 4, 6 to 11. Actually, I'm lying, I need 12. It's 12. Lovely, and press Control Enter. Estimates the logical transformation, then I apply it. And I can use the autoplot command to make sure everything looks sensible. So over here we can see CD4, CD8, CD3. So everything looks all right here. Looks fairly typical. As the settings are very high, or the transformation has put the settings very high. But that's something you can look into in the future. Okay, so we're going to do the automated gating. So exactly the same as we did before, just in an automated manner. So again, we're going to create an empty gating set called AutoGS. And then we're going to load data into AutoGS, into FS data, using this GS population get the data command. And so you should read the help documentation about gating sets, because the gating set doesn't contain any actual FCS information. It's just a structure for the gating information. So whenever you want to analyze your data in a gating set, you actually have to load the data first. And we'll discuss this again later on in the statistics section. So I'm going to create a non-debris gate. I'll be using fs apply. So fs apply is something we came across earlier, which is a way to iterate through all the files in a gating set, in a flow set, the data, the function, and we're going to be using OpenCyto. So OpenCyto is another package that allows you to use clustering algorithms effectively to get your information. So we'll be looking at flowClust2D on the flow frame, and this FR for flow frame comes from the function here, and the channels forward scatter area and side scatter area. So on this flowClust2D, there's lots of auxiliary commands, and as usual, if you ever want to find out other commands to add to it, use $flowClust2D, and then it'll give you a list of possible variables or arguments. And if you ever have an issues, you read through this and find out if you should change any. And quite often, you'll find you want to maybe add a min. If you have a lot of debris, you can say it to only look at cells over a certain level. But anyway, we're going to trust it and we're just going to go for it. So it's looking through channels forward scatter area and side scatter area. And then it's giving me some errors here, but these are not of a concern at the moment. It's saying that the default for the clusters is number is 2. And when we have used prior, there's no effect, so that's fine. And then we're going to use this gating set population add to my gating set, AutoGS. I'm going to add the non-debris gate to the parent root and give it the name non-debris gate. So that is exactly the same as a manual one. Gives me 2, I can recompute. And this time, instead of using ggCyto implicitly, I'm using its autoplot feature. So I'm going to autoplot, AutoGS, x and y parameters, non-debris gate, and the number of bins, so that's the density of the dots. And we can see from my 2 files, it's very nicely picked up these 2 populations. I mean, the data is quite clean to start with. Very suspicious oval shape here, but whatever. So anyway, let's keep going. I shouldn't digress. Next, we're going to do a singlet gate. So again, we're going to use the data. We're going to extract the data, but this time with only the non-debris gate. So not of root, but of the non-debris gate only. Create something called singlet gate, use fsapply, use a different function. So from OpenCyto, we're going to use singlet gate. If you want to know more about OpenCyto, you use the help documentation again, $OpenCyto, and this will give you different ways of interacting with OpenCyto. Okay, so we'll do forward scatter area versus forward scatter height, which this file thankfully does have. And again, we'll use the GS population add. Parent is non-debris gate this time, and the new name is singlets. We can recompute, which recomputes all the statistics, and use autoplot, but this time looking at the singlet gate, using it forward scatter area and forward scatter height. And you see it works out quite nicely. One of the biggest issues with autoplot, by the way, is it always puts the statistic figure on top of your gate. So on this, it's not the end of the world, but if you've got lots of plots, you'll end up with just lots of pictures of numbers, which is why you want to use ggplot implicitly, or call it implicitly. Okay, let's do a quadrant gate. So again, we're going to get the data from singlets this time. Then we're going to create a quadrant gate, fsapply, function, OpenCyto. There's 2 quadrant gate commands, quadrant gate sequence and quadrant gate tmix. Look at the documentation. Sequence wants a function to how to apply, work out where the breakoffs are, and I'm using min density today. And I'm using a minimum of 3 and 3. So I know this already because I did a run through and there was issues because there was so much debris. Well, there were so many negative numbers that it was confusing the quadrant gate. So I did a little bit of troubleshooting and used this min command, and I'm using the channels FitCA and P Texas Red, which I think is CD3 and CD4. And then we're going to use the gate accept population add again. So here's a strange thing about this data. Normally, you do not have this naming command when you produce a quadrant gate, because it would automatically create a CD4 positive, CD3 negative, CD3 positive, CD3 negative, etc. gating structure. But for some reason, for this data, it's not working. And only this data, I can't recreate it with anything else, I don't know why. So I'm going to give it a name, and again I use the C command to group lots of numbers together. I'm just going to call them gates 1, 2, 3, and 4 because it makes my life easier. So it creates gate quadrant 1, 2, 3, and 4, and which are gates 4, 5, 6, and 7. Okay, not so simple to understand. Recompute. I can look at the paths and I can see that I now have these extra gates. I could type in plot, AutoGS, and I can see a nice structure, and I can use autoplot to have a look at these gates. So I'm using, instead of typing in 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4 like this, I'm using the GS get the population paths 4 to 7, because it's number 4, 5, 6, 7, so we can see them all at the same time. There's no way to get all 4 quads at the same time without specifically calling them. Now here we have an issue, and we can see that autoplot is not displaying the maximum values properly. It doesn't look great. So I knew this was coming, so I've already prepared a fix. So we're going to be using GG Cyto, and I say there'll be another video about this, but this is the same way as you produce a plot using the ggplot package. So I'm going to use my files gating set. I don't really need 1 to 2 there, never mind. AES stands for aesthetics, and there's some X and Y parameters. My subsets are singles. Creates a variable called P, which has my gate in it. I want to use 256 bins, so that's my density. I want to add gates 4 to 7. I want to add the statistics 4 to 7. I'm using this theming. Actually, I don't need the theming, I'll ignore that. This theming changes the size of this text. For previous analysis I was doing, this text didn't fit into this box, so I just made it smaller. And what I'm going to do is I'm going to artificially choose my X and Y parameters. So this is going to be this myPars command using the GG Cyto par set. And my limits for the Y and X axis are 3 to 5. I'm going to apply myPars to my picture, and then I'm going to load the picture by typing P. And there we go. We have some nice gating. It's worked quite nicely. There's a few other commands you could do for Quadrant. You could specifically say, I think my first cluster is here, which is quite useful if your clusters aren't well defined. You could obviously do this to a single to your control and then apply it to all of them. So at the moment, because we're using fs apply, each file is getting its own analysis looking at density, which might not be ideal, and in the better world you'd be using your controls. So you would do this automated method to one file and apply it to all the subsequent ones. Okay, so let's have a look at a few other commands. So number 1, if you want to remove, if you make a mistake, you can use this gating set population remove command, and you can ask which gate you want to remove. Sadly, you can't group more than one gate at a time, so you have to do one at a time. Next, we can look at statistics. So again, we've done this before. These are the counts, these are the percentages, and there's a few different, so instead of percent, you can type in type, population MFI, which will give you the MFI of each column and of each gate. I've got each gate because I'm telling it to load every single one here. I could have changed that to say the non-debris gate, or maybe to 1, and I wouldn't get so much data. You can add functions on this type. You can apply a function. So this is the example from the help file. The help file is, as ever, 2 question marks and the command. And at the bottom, we can see this example of using the quartile. So you produce a new function. If you want to learn about functions, you should do a general R course. And I can apply this new function here. And this will create a new statistics output here with my new function. One thing to be wary of is each parameter is a different column. So if you want to make your own function, for example, I've made one here for means. You would, if you were unaware of this, you would probably just use the rmeans command, but this will just produce a mean of all the data. So that's all the data in every single column and produce one number, and you would get an error in this case. And what you actually want is the column means command, because then it does a mean of each column. So that's a new population means function, and now I can get the mean of each of these. If you want to do things like geometric mean, these all exist in R already, and you can just make a new function using this command. Okay, that's it. If you want to put these into a CSV file, use the write CSV command, which is another base R package. And yeah, that's it. Just play around and definitely look at the documentation here and search Google, look in the bioconductor pages. There's lots of good examples and tutorials. Just be aware that in the last few months, all of these names have changed. So you will get an error if you type in the wrong one, and it'll tell you which one to type in. Okay, thank you. Goodbye.